So welcome. We're going to work on Unit 4, Lesson 2, one-to-one functions, and also inverse functions. So this is Chapter 6, Section 2. Remember, we've already defined what a function was, so let's just kind of review that again. Definition of a function. Remember, a function exists when input values, which we also call the domain, go through a series of calculations, which now we know are also called polynomials or rational functions. And the result is what we call these output values or the range. So an easy way to identify if something is a function is if I give you a set of ordered pairs, the x values cannot repeat. So if I give you a set of ordered pairs or a table, the x values can't repeat. If I give you the graph, remember the graph must pass the vertical line test to be a function. Now, a one-to-one function is a special function in which the y values must also be connected to exactly one x value. So notice how in a function, the x values must be assigned exactly one output value. Now, the y values must also be connected to exactly one x value. So we can only be assigned one value. So what this means as well then is the y values can't repeat either. And this also means from a graphing perspective, it has to pass what's called the horizontal line test to be a one-to-one function. So remember, when drawing a horizontal line through the graph, it must intersect the graph only one time. If it intersects more than once, then that's not going to be a one-to-one function. So to be a one-to-one function, the x values and the y values can't repeat. And the graph must pass both the vertical and the horizontal line tests. Now, to kind of grasp this, we use kind of mapping to start with. Notice how this 6 is assigned two different y values. That does not meet the criteria of a function. Each x value can only be assigned one y value, not two. And if we make a set of ordered pairs here, you should see that there's a 610, there's a 611, the 7 goes with the 12, and the 8 goes with this 13. So notice though the 6, the x value is repeating. That cannot happen in the definition of a function. So this mapping here does not represent a function. So, I mean, we can graph it, but it does not represent a function. But look at this next example. Notice how the 3 is assigned to a 7, the 2 is assigned an 8, a 1 is assigned an 8. So notice how each x value is only assigned one y value. So if I look at the order pairs, I have this 3, 7, we have this 2, 8, and we have this 1, 8. Notice the x values are not repeating. So this is a function. But now if I look the other direction, you know, the y values, the 7 is paired to a 3, the 8 is paired to a 2, but notice how the 8 is also paired with this 1. So from the perspective of a one-to-one function, this is not a one-to-one function. The y value cannot be assigned two different x values. And notice how you can see it in the table or the order pairs, this 8 is repeating. That cannot happen in a one-to-one function. So yes, this is a function, but not one-to-one. So if I look at this next example, notice how the 4 is paired to the 3, the 8's paired to the 5, the 10's paired to the 7. Each x value is paired with exactly one y value. So notice how we have this 4, 3, we have this 8, 5, and we have this 10, 7. So notice how the 4, the 8, the 10, there's no repetition in the x values. So this is a function. If you go the other direction, 3 is assigned to 4, the 5 is assigned to 8, the 7 is assigned to 10. So notice that if you go the other direction, the y values are only associated with one x value. And if you look at the order pairs, there's not a repetition in the y values. So this is a one-to-one function. It passes both of those. So if I look at this set of order pairs, -2, 6, -1, 3, 0, 2, 1, 5, 2, 8. If you look at the x values, -2, -1, 0, 1, 2, they're not repeating. If you look at the y values, 6, 3, 2, 5, 8, they're not repeating. So this would be an example of a one-to-one function. Now, from a graphing perspective, notice that we have these two graphs here. If you look at the first one, notice how it does pass the vertical line test, so it is a function. But is it a one-to-one function? So if you draw a horizontal line, notice that the horizontal line just touches the graph in one spot. So this graph represents a one-to-one function. If you look at this next equation, this parabola, notice that it does pass the vertical line test because parabolas are functions. But if you draw a horizontal line, notice that this horizontal line does intersect the graph in two spots. So it does not pass the horizontal line test. So this is not one-to-one. So it is a function, but it's not a one-to-one function. So that's kind of where we're heading with all this. So why do we need to have a one-to-one function? Well, this is where the inverse function comes into play. When working with one-to-one functions, what can exist is what's called an inverse function. Now remember, inverse kind of means going backwards. So if you're given a one-to-one function, its inverse can be found by thinking backwards. So what happens here is the role of the domain and the range, the roles of the x's and y's will trade places. So as we move forward, if f of x is a one-to-one function, then f of -1x represents its inverse. Now we have talked about negative exponents, but f of -1 of x, that does not equal 1 over f of x. That's not the same thing. So this is just a notation that means we have an inverse function. So don't confuse it with a negative exponent. It doesn't actually mean that here. So when given a function f of x, remember its order pairs would be like x, y. The graph of its inverse can be determined by switching the x's and y's. So the y becomes the x and the x becomes the y. So that's how I can graph an inverse function, is just switch the rows of x and y in the original function. Something else to be aware of is the function and its inverse will always be symmetric to the line y equals x. So when you graph both of those on the same graph, they should be symmetric to the line y equals x. And remember, these are the critical order pairs in graphing the line y equals x. So -1, 1, 0, 0, 1, 1, those are your critical points in graphing that. So the graph of a one-to-one function is given. We want to create the graph of its inverse. So we want to graph f of -1. To do that, if we look at the function f of x, its x values and its y values. So notice how we have this -2, -2 as an ordered pair. We have this 0, -1 as an ordered pair, and we have this 2 and this 1/2 as an ordered pair. Again, I like to write the ordered pairs in more of a form of a table, just like the graphing calculator does. The inverse function, its ordered pairs are going to be the rows of x and y switched, but when you both are -2, you can't really tell much going on there. Notice that 0, -1, though, that's going to now turn into -1, 0. And this 2, 1/2 is now going to turn into 1/2, 2. So if I want to graph the inverse, all I have to do is graph those 3 ordered pairs to start with. So -2, -2 has already been graphed for us. It's there. -1, 0 would be located here. And 1/2, 2 would be located here. There's another point there I missed. Looks like 1, 0 would also be a point. So 1, 0 would also be like 0, 1. So there's 1, 2, 3, 4 ordered pairs. So we should also have a 1, 0. So 1, 0 is now going to be this 0, 1. So let's plot this fourth little point. Okay. So if we recognize that all we got to do now is just kind of construct the graph now. Let's see here. Get situated here. Come on, you can race. Okay. Try that again. So if we graph this, we have that, and then we have that. Not too bad. So notice that this line y equals x, there is symmetry with respect to the line y equals x. Notice how it kind of mirrors itself across that line there. So that's a good tool to help us create the inverse graph. So if we have the given function graphed here, if I want to identify the ordered pairs of the inverse function, all I have to do is switch the rows of x and y. So -1, -1, well, that's still going to be -1, -1. 0, 0 is still going to be just 0, 0. So that's going to be a little tricky. But 2, 1 does change. That's going to be now 1, 2. So 1, 2 would actually be here. So this is where the line y equals x also comes into play. The symmetry kind of helps me see this. So notice how this mirrors over here. This graph kind of bends out this way. It crosses and then bends out this way and comes back in. Notice how the graph is symmetric to this line y equals x here. So it kind of helps us see the graphs as inverses. So that's how we can go about graphing an inverse function if we know the actual one-to-one function. So verifying that f and g are inverses of each other. So as we move forward, we're going to start trying to find a function and its inverse. Instead of using f and f of -1, a lot of times, g of x is going to be in place of f of -1 of x. It's easier to write. So a lot of times we're going to say f is a function and we're going to say g is its inverse. Now, for that to really be true, for this to hold true, f of g of x has to equal x and g of f of x equals x. If that does not happen, then f and g are not inverses of each other. But if this does happen, if both f of g of x equals x and g of f of x equals x, that does prove that these two functions are inverses of each other. Now, remember, if you're thinking backwards, a lot of times I'll use the analogy of just getting dressed. For me, shirts on, pants on, socks on, shoes on. If I reverse that, first thing I would do would be shoes off, socks off, pants off, shirt off. You just reverse the processes. That's inverse thinking. So if you notice here, if I look at the function f of x, notice if you look at where x is, to evaluate the function, you'd have to multiply by 3 and then add 4. The inverse function has to undo that. So the last thing was adding 4, so that should be the first thing I undo is subtracting the 4. The first thing I did was multiply by 3. So to undo multiplying by 3, we would have to divide by 3. So if you look at this function over here, g of x, notice how we now have subtraction of 4 in parentheses. That's got to be done first. And then multiplying by 1/3 is like dividing by 3. So I kind of like that. So let's move on and see if we can actually prove these are indeed inverses of each other. So first off, we have to evaluate f of g of x. And what I'm hoping for is it gives me x. Let's see here. So to evaluate f of g of x, we first have to identify what g of x is. This looks like a handful to put in for g of x. So I'm going to multiply the 1/3 through and make this 1/3 x minus 4/3. That's not much better, but at least I don't have all these parentheses. So this becomes then f of 1/3 x minus 4/3. So what I got to do now is I have to replace 1/3 x minus 4/3. I'm going to substitute that in for x in the f function. So this here is going to get substituted in for x up here. So this becomes then 3 times 1/3 x minus 4/3 plus 4. So to evaluate this, I have to multiply the 3 through the parentheses. But when I do that, what I like to do is I like to start with the denominator. So I go 3 goes into 3 one time, and 1 times 1x would just be 1x, or we just write that as x. 3 goes into 3 one time, 1 times -4 would be -4. So the parentheses are now removed, and then I just add this 4 in there. And notice how -4 and a 4 will zero out, and that gives me x. So it does pass the first test. F of g of x does equal x. So the next thing we want to do is we want to figure out what g of f of x is. Now f of x is this 3x plus 4. So this becomes then g of 3x plus 4. Now the 3x plus 4, this here has to go in place of x up here. And I'm going to use this version of it off because it looks like that one's actually easier to work it there. It doesn't matter which one you use. I just prefer to use this one here. So I could have also used this x here if I wanted to. So I'm going to have 1/3 times, and I'm going to replace x with 3x plus 4. And I have this minus 4 still. Notice how the 4 and the -4 will zero out. That gives me 1/3 times 3x. And also 1/3 times 3x, the 3's divide out, and that just leaves me 1x, or we just call that x. So since we both of those gave us x, you know, since we now proved that f of g of x equaled x and g of f of x equaled x, what this means is this: f and g are inverses of each other. So as we move into this next one, notice how we start to deal with cubes and cube roots and things like that. If we want to make a little note here, inverse operations that cancel each other out. Notice how if we have square root and square, those are inverses of each other. So square root and square cancel each other out, and it just leaves me x. If I have the square root of x squared, that also is the same thing. The square root and the x squared cancel each other out, and that just leaves me this x. Similarly, the cube root of x cubed, those are inverse operations, and that just becomes x. Those cancel each other out. Or if we have the cube root of x cubed, again, those are inverse operations. They cancel each other out, and that gives us x. So as I move into this lesson up here, if I want to verify that these are indeed inverse functions, one thing to pick up on is this, I'm cubing and then subtracting 8. The inverse should be adding 8 first. Well, notice how we have x plus 8. And then the cube root is the inverse of cubing. So I'm really thinking these are inverses just by observing that situation. But they want us to verify this. So let's evaluate f of g of x to start with. So what happens is we identify g of x as the cube root of x plus 8. So this becomes f of the cube root of x plus 8. And then the cube root of x plus 8 goes in to the other function. So now I'm using the f function. This here will now go in place of x here. So this is going to become then, in parentheses, the cube root of x plus 8. And that's raised to the third power minus 8. But also have cube root and cubing are inverse operations, so they cancel each other out. And that leaves me with x plus 8 minus 8. And then the plus 8 and the minus 8 will zero out, and that leaves me x. So that passes that. F of g of x does equal indeed x. So to verify this further, though, we have to prove that g of f of x equals x. So now we have to identify what f of x is. That's going to be the cube root of x, or x cubed minus 8. So this becomes g of x cubed minus 8. And note that this x cubed minus 8 has to go in for x here. So this now becomes then the cube root of, and then I replace x with x cubed minus 8 plus 8. Notice how if I simplify this, the minus 8 and the plus 8 will zero out. So I'm left with the cube root of x cubed. Well, that's going to cancel each other out, and that leaves me x. So g of f of x does indeed equal x as well. So these are indeed inverses of each other. So f and g are inverses. So the last thing we want to do in our assignment is, for the following one-to-one functions, we want to find the inverse and verify the answers are indeed inverses. We then want to find the domain and range of f and its inverse, and we want to graph the functions on the same graph. It may be easier to get the domain and range from the graph, so I may go ahead and graph before I do domain and range. So that's how we're just given the function f of x equals 3x minus 1. So this is the same thing as y equals 3x minus 1. So to find its inverse, f of negative 1 of x, so to find that inverse, what we have to do is we can do is switch the places with x and y and then solve for y. Notice though, I'm just using my logic, the function says multiply by 3 and then subtract 1. To undo that, I need to add 1 and divide by 3. So inverse function should be x plus 1 divided by 3, just using some common sense. So if I want to find the inverse, though, our first move is to switch the rows of x and y. So this means this becomes x equals 3y minus 1. So where there was a y, we changed to an x, and where there was an x, we changed to a y. Now our strategy is to solve for y. So again, we have to get rid of the -1, so we can add 1 to each side of the equation. But x plus 1 are not like terms, so they just come down as 1, 2 pieces equals then this 3y. And then to get rid of the 3, we have to divide both sides by 3. And so therefore we end up with x plus 1 over 3 equals y. So the inverse function would be then x plus 1 over 3. That's kind of what we thought. So notice how our original function, we multiplied by 3 and subtracted 1. The inverse has to undo that. So it has to add 1, then divide by 3, and that's what it's doing. So again, to find an inverse, if they get more complicated, switching the rows of x and y and solving for y would be a better strategy. So before I go further, I want to go ahead and verify these answers. So we have to have f of x. So f of x is going to be this 3x minus 1. F of -1 of x, I'm going to let g of x equal that. And so we're going to let g of x equal this x plus 1 over 3. I think that notation is going to be a little bit easier to deal with. So to find the inverse function or to verify it, we want to first figure out what is f of g of x. And it has to equal x to start with. That's how we verify this. So this is going to become then f of x plus 1 over 3. And then the x plus 1 over 3 has to go in for x in the f function. So again, the x plus 1 over 3 has to go in for x in the f function. So this becomes then 3 times x plus 1 over 3 minus 1. Notice how the 3's will divide out, and that leaves me then with x plus 1 minus 1. The plus 1 and the minus 1 do 0 out, so that gives me my x. So the first test works. F of g of x does equal x. But what also has to hold true is g of f of x must also equal x. So f of x is going to be this 3x minus 1. And then I have to substitute that 3x minus 1. This 3x minus 1 has to be substituted into the g function, or the inverse, if you will. It's got to go in place of x there. So this becomes then 3x minus 1 plus 1 over 3. So if I simplify that, the -1 and the plus 1 will 0 out. I have 3x over 3. The 3's divide out, and that gives me then x. So what we pick up on is f and oops, lost it there. Come back here. Let's see here. Okay, so f and f of -1 are indeed inverses, as we verified it by proving f of g of x and g of f of x both equal x. Now, as far as graphing goes, I'm going to use the original function is going to be f of x equals 3x minus 1. I'm going to graph that first. So in graphing f of x equals 3x minus 1, I'm going to just use a table to graph it. So I'm going to have 0 goes in, 3 times 0 is 0, minus 1 is going to be a -1. 1 goes in, 3 times 1 is 3, minus 1 gives me 2. If 2 goes in, 3 times 2 is 6, minus 1 would be 5. So let's graph those 3 points. 0, -1 would be here. 2 was, or 1 was 2. So 1, 2. And then we have 2, 5. So your line would be going through here like so. So that would be the graph of that function. Notice how it does have a y-intercept of -1, and the slope is 3, so it's a rise up 3 and over 1, rise up 3 over 1. So that does check out that we have the correct graph there. Now to graph the inverse, what I want to also draw in here is the line of symmetry, that y equals x line. So remember -1, 1, 0, 0, 1, 1. So that line of symmetry would be coming across here like so. So we're going to use that as a guide, that line of symmetry. Notice how we have this point 0, -1. So our new point is going to be -1, 0. The point that was 1, 2 now becomes 2, 1. And the point that was 2, 5 now becomes 5, 2. So let me do that in a little bit different color there. So we have -1, 0. We have 2, 1, and 5, 2. So this graph here should go across like so. And notice that it does look pretty symmetric to the line y equals x. Yours probably should look a little bit better than that than mine. But we do have the graphs there. So notice that the domain and range, since these are lines, there aren't any domain or range restrictions. So if I write down, then we have this, we have so we have f of x equals 3x minus 1. Its domain and range, since there's no left bound and no right bound, -infinity to infinity. The range, again, there's no lower bound or upper bound, so -infinity to infinity. When I look at the inverse function, that x plus 1 over 3, its domain and range is also going to be the same. So it's going to be for -infinity to infinity and -infinity to infinity. So there's not any domain or range restrictions there. Let's try to do one more of these. So in graphing this, well, we'll save that for last, but first off, we want to find the inverse. So that find the inverse, the first thing I'm going to start with is, I'm going to write this as y equals x cubed plus 4. But my next step is to switch x and y. So the y becomes the x and the x becomes the y. So then we solve for y. So to solve for y, we have to subtract 4 on each side of the equation. So we have x minus 4 equals y cubed. And to get rid of cube, we have to take the cube root of each side. So I have to take the cube root of x minus 4. Oops. Let me just keep the x minus 4 in green. And we have to take the cube root of y cubed. So this becomes then the cube root of x minus 4. But also how the cube root and cubing cancel each other out, and that just leaves me with y. So therefore, my inverse function is going to be the cube root of x minus 4. And that makes sense because if you notice our original function is x cubed plus 4, the inverse function should subtract 4 to start with, and then to undo cubing, we'd have to take the cube root. So that does make sense. That is our inverse. Now, to prove it, to verify, we have to evaluate f of g of x. So again, I'm going to note here that g of x is going to be used as the inverse here, so I don't have to use that f of -1 notation. So I have to evaluate f of g of x to start with. So g of x is going to be the cube root of x minus 4. So I have f of the cube root of x minus 4. And remember, that's got to be substituted in to this function up here for x. So we got to replace this x with the cube root of x minus 4. So this becomes then the cube root of x minus 4 goes in place of x, and this is still cubed. And then we had this plus 4. Notice how the cube root and cubing are going to cancel each other out, and that's going to leave me this x minus 4 plus 4. And the minus 4 and the plus 4 do zero out and give me my x. So that's done. F of g of x does indeed equal x. So now I have to evaluate g of f of x. So again, f of x is going to be that x cubed plus 4. And it has to go in place of this here, has to go in place of x in our g of x function, which is a little bit higher though. There we go. It's going to be right there. So this becomes then the cube root of, oops, go back. So this is going to be the cube root of, and we're going to replace x with x cubed plus 4. And I have that minus 4 still to deal with. So this is going to become then the plus 4 and the minus 4 will zero out. This gives me the cube root of x cubed. And since those are inverses of each other, this does give me x. So g of f of x does indeed equal x. So f and its inverse are actually really are inverses. So to graph this, I'm going to again look at f of x equals x cubed plus 4. You should recognize this as a snake that's been shifted 4 places up. So really, to graph this, I need to understand x cubed. So x cubed remember, if we put 1 in, we get 1. If we put 0 in, we get 0. If we get -1, we end up with this -1. So to graph this function, though, x cubed plus 4, we recognize that this is a vertical shift. So the y values are shifted up 4. So 1, 5, 0, 4, and -1, 3 would be the order pairs. So when I graph x cubed plus 4, those are the 3 order pairs that I want to graph. So 1, 5, 0, 4, and negative 1, 3. And remember, this is a snake, so it kind of goes it down and it kind of flattens out here through the 4 and then turns and goes across this way. Now, to help us graph the inverse, we also want to draw the line y equals x in here. So that's where we have the negative 1, 1, negative 1, 0, 0, 1, 1. So our line kind of goes through here. So to graph the inverse, and I'm going to use a different color for that. So this order pair negative 1, 3 becomes 3, negative 1. The order pair 0, 4 becomes now 4, 0. And the order pair 1, 5 becomes now 5, 1. And so now this graph kind of snakes off this way. It runs along the x-axis, bends down, and flattens out, and takes off running in that direction. And notice how the graph does look symmetric to the line y equals x. It kind of folds over, or it's mirrored over the line y equals x. So that does check out. So what are we left with? Domain and range. Notice there is no domain restriction, and the lower bound is an arrow and the upper bound is an arrow. So the domain and range on both of these, again, are the set of real numbers. So there's not any restrictions on these two functions. So if I write down the function f of x, oops, let me clean that up a little bit. So f of x equals x cubed plus 4. Its domain is going to be from negative infinity to infinity, and the range is also going to be from negative infinity to infinity. For its inverse function, which we said was the cube root of x minus 4, it's also going to have no domain restriction or range restriction. So it's going to be the set of real numbers for both of those. So the domain is going to be negative infinity to infinity, and the range is going to be negative infinity to infinity. So we have that kind of going on. So that kind of takes us through lesson 2. You have a good day.